Hello, everyone. Hi, my name is Amir, and I'll be talking to you today about how we make Alexa smarter. But before I start my talk, I hope that you guys all had a fantastic time today. It's great to have many of you here. And thanks for the organizers as well. Such a great venue with so many great talks. It takes a little dedication to do that, so thanks for all the organizers. So I'm part of the Alexa team in Cambridge in the UK. Alexa has a big presence there in terms of all the different components that we build. However, a big part of the team that I'm part of is responsible for making Alexa smarter and more intelligent. It's specifically focused on open domain dialogue and open domain question answering. And when I say open domain, it means that you don't have any restrictions on what kind of topic you're talking about. As you saw in some of the previous presentations, so when you build skills for Alexa, you could encode some of the behaviors by keywords or some specific annotations that when Alexa hears that, it will respond. But we work in the opposite side of it, which is very free, open dialogue with Alexa. And of course, there are many, many big challenges in there. Right now, Alexa is a global device, and I'm sure you've seen some of the ways that Alexa works. But in a very high level, Alexa has an onboard signal processing system that detects the wake word, and when you call Alexa, however, all the processing happens in the cloud, and it mainly goes through 4 steps. So one is to transcribe your speech. So when you speak, it will try to translate that to text. We will have a system that is called natural language understanding, where it tries to understand what you said when you talk to Alexa. Based on that, it will try to have some responses generated. We have a dialogue management system that tries to keep the track for what you're speaking and take in turns if you're having a dialogue. And finally, you have a text-to-speech system that tries to speak back the answer or the action that Alexa is doing. And Alexa is today a global system, so it's available in more than 80 countries. We have more than 14 localized experiences for Alexa. So in order to actually scale to this many users and this many languages, you have to be able to actually utilize a lot of the advancements in machine learning, deep learning, and AI. And it's predominantly the kind of systems that we develop in Cambridge. For Alexa to become a true digital assistant to you and a smart companion, she needs to understand what you say. She needs to be able to respond and act accordingly, and with a full knowledge of the world that she lives in and we all live in. So I'll go through some pieces from this text to actually explain what I mean. So. First of all, understanding, what I mean by understanding is that when she hears you, she needs to parse what you said, try to build a picture of actually what you asked her to do, or what was the question. Understanding on its own isn't a separate phenomenon. So when we speak to each other in human to human, you have a lot of context about the world. You know what I'm often talking about implicitly. So in order for Alexa to understand, she needs to have access to accurate knowledge of the world. And when I mean accurate knowledge, it means both factual, knowing that, for example, Gdansk is a city in Poland. So that is a fact in the world, and she needs to know that to be able to answer your question if you have any questions, let's say, about Gdansk. But also about how the world works. So she needs to know that, for example, humans can't fly unless they are on an airplane or a helicopter. So, or you need air to breathe to live. So these are things that is based on mechanics of the world and physics of the world. And again, as humans, we all are quite knowledgeable about that. However, for Alexa to be able to again respond intelligently and grounded to the world that we live in, she needs to also know how the world works, what's the mechanics of the world. And the final part is really about dynamism of the world as well, because our world is not static, so it's not that it's just one snapshot of all the things. World is dynamic. A lot of things happens. A lot of events happens. We discover new facts about the world. So Alexa needs to be able to actually acquire knowledge at a very high scale and adapt quickly to how the world is changing. And if you decompose all of this, you have some series of big components, such as knowledge acquisition, being able to do self-learning, meaning that, again, adapt to the world very, very quickly, teach herself about new things in the world. She needs to understand us, and finally, be able to provide us with an answer or an action. So today, most of my talk is going to be about knowledge acquisition. However, there are many, many pieces of systems that needs to actually run in parallel and in high accuracy to enable Alexa to behave intelligently. To start with, and to explain you some also why this is a difficult challenge, you can start with some simple questions that you could ask Alexa. You might ask Alexa, how long is a gherkin? And many of you know gherkin is a pickled vegetable, cucumber, which we may use. And then I think Poland actually make very good gherkins as well. But depending on where you are, this question actually could be interpreted very, very differently, because I don't know how many of you know this building, but there's a building in London which is also called Gherkin. And you could also ask the question, how long is a gherkin? So you could see that there is lots of ambiguity in how we speak, and it's very natural again for us, depending on the context and which situation we are. We immediately know what we are talking about, but for Alexa, she needs to have also this contextual understanding. So if, for example, she's in the UK, she may actually prefer to interpret gherkin as more about the building, not the pickle. Some of this context could come also from the question itself. So you may have, Alexa, is gherkin taller than the Shard? And in here, the Shard is another building, so it's the building on the right-hand side, which is also another skyscraper in London. So again, here, you could use the context in the sentence, knowing that the other part of the text is talking about the building. So hence, this gherkin could be the building that I'm talking about. So there's lots of these kind of intelligence that it needs to have to be able to actually understand correctly what you're talking about. Similarly, we could look into more examples. Alexa, how far is the nearest star? And Alexa, how far is the nearest Starbucks? And again, depending on just the last few pieces of text in here, so basically the box, the understanding and the action that you desire from Alexa is totally different. So from the first one, you want to know how far is the nearest star, which hopefully should be our sun. And with the other one, you are more looking for a location, and you're looking for a coffee shop, and you're asking actually about how far you are from the nearest Starbucks to run and have a coffee. So again, Alexa needs to not only understand what you're talking about, but also decode exactly what is the target of the question that you have. And there's endless number of these kind of questions and situations where there is severe ambiguity, and you need to be able to actually truly understand language and truly understand human beings to be able to answer correctly. So let's start with an example. I'm going to use this example throughout the talk to actually demonstrate how this actually comes together. So you could ask Alexa, when was the last Star Wars movies? And if you ask her, she will say back that the most recent Star Wars movie was Solo, a Star Wars story, which was released on 25th of May, 2018. So how does it happen? What happened here in terms of mechanics behind the scene? So first of all, Alexa needs to detect from this text that you're talking or you're asking a question about Star Wars movie. So she has to have a concept of what is a Star Wars movie. And she has to also know that there are many of them. It's not just one movie. So there are many, many of these films. She needs to be able to detect that you're talking about temporal concepts here. So you're talking about when, and this is a temporal concept. And she needs to be able to also know that you were asking for the last one, not just any of these films. So if I gave this example to you as a developer, and I'm sure many of you have technical skills to start looking into how to solve this, probably the kind of approach that you may have is that if I had a database that had all the films in it and had all the publication dates, the dates of those release dates of those films, then I could potentially write a rule to go through that database, bring all the movies, sort them based on time, and then pick the most recent one to get back to me. Again, that kind of rule-based behavior doesn't scale to all the situations that you want to cover, so you need to use machine learning to actually be able to do this. But I'm going today to talk more about actually what is the behind the scene in terms of that database that you access to, because again, you have to store all this information, all this knowledge in a form that is easily accessible for Alexa. So we are going to talk more about the knowledge side of it rather than actually how to decode this sentence into a query for this database. So a concept that we potentially some of you know, but I'll give an introduction to it, is called knowledge graphs. So knowledge graphs are basically kinds of databases, so a repository of knowledge that is not similar to, that encodes basically a lot of the relationships between concepts in the world. So in here, you could start with, let's say, Star Wars as a franchise. So this is a thing in the world, it's a concept in the world. There are Star Wars film series. So these are all the films that have been published under Star Wars franchise. You have the Solo, the film that you were talking about, as another entity here. There are edges between these two. We call these relationships, which express what kind of relationship these two entities have. So for example, Solo Star Wars Story is a film which is part of a series of Star Wars film series. The same way, Ron Howard is the director of the Star Wars film. So you can express the knowledge of the world by concepts. So these are nodes. So these are these kind of dots here. And the relationships that exist between all of these entities, such as who's the director, what kind of concept this is, who created the Star Wars franchise, and etc. So this is often called a knowledge graph. And behind the scene, we have a few big knowledge graphs that power Alexa's intelligence. As I mentioned, this is a formal definition of a knowledge graph. So it's a directed graph with nodes representing these entities and relationships, or sometimes attributes, so such as how high is a building is an attribute, so it's a property, like how many meters. And together with knowledge graph, there are also another concept called ontology, and ontology often tells us the kind of concepts that we are talking about and what kind of relationships they could have. So as an example, you could think of like humans as a concept, as a class in our ontology, and we know that, for example, a human can have a mother and a father, biological ones. And these are basically kinds of relationships that are allowed between all the different classes of entities. So ontology actually more or less encodes our knowledge of how the world works. So the mechanics of the world often gets encoded inside ontology, and having a very robust and big ontology actually helps you to describe a lot of things in the world within the knowledge graph. One of the publicly accessible knowledge graphs is called Wikidata. I'll come back to it later, but again, within the context of this question that we were talking about, so the Star Wars film, the Solo film, is an entity, so and has an ID and has a bunch of properties underneath it. So this is how you, for example, see some parts of the knowledge graph described to you. So you could see, for example, that has labels, meaning that that ID may be referred to as Solo Star Wars Story, or maybe in Korean language it may be called that, which I can't pronounce. But you basically encode all your knowledge about this entity in a graph and a relationship that you can see. For example here. You could have particular relationships. So for example, P31 in Wikidata is an instance of, and the ID Q11-424 is the film. So by knowing this relationship, you know that this concept that you were talking about is actually a film. It's part of an instance of a film class. Or, for example, you might see something like that. So P177, 577 is the publication date, and then here's the publication date for that film. So you can see example of how really the knowledge graph actually represents entities in the world. So the question comes that how these knowledge graphs are built, how we can actually build one of these, and then traditionally knowledge graphs are built manually. Through great efforts. So, for example, Wikidata that I mentioned to you is a collaborative, what it's called collaboratively edited knowledge base. There are actually humans that go in there and actually write about these entities and describe what kind of relationships they have, etc. It is title linked with Wikipedia, where again people go and write about entities and the concepts in the world. But Wikidata is actually one of the largest and most up-to-date knowledge graphs in the world, but it's predominantly done by hand, which I think is good if you are really thinking about rather smaller scale and very, very small incremental update to the world, because again, if you are a human and you have to go in there and write about it and do all these checks and etc., it's quite a slow process, so it's not going to scale to really the world that we live in, and it can't adapt quickly to the world that we have. So then the question comes that, how can you actually do this through machine learning? How can you actually acquire knowledge of the world and then encode it in a knowledge graph? So we can, of course, look into web, and web is a great source of knowledge. So, you can start from, Wikipedia to, maybe movie reviews, to, specialized websites such as IMDb, where they talk about, films. To also more, free-flowing side of it, which is, maybe some Reddit or any other forum that they discuss about, things in the world. So web is a great source of information, and we tap into it to actually make Alexa smarter. But more and more, there are other forms of mediums, forms of information that we need to be able to actually also look into it and actually extract information from it. So again, in the context of this film, there may be podcasts that somebody is talking about this film, so you might want to actually go through that and actually understand. Maybe there are new facts or new information there. There are videos that people again talk about films and reviews. And again, here I'm using film really because of that example that I started with. But this, you can think of this across the board, across all the topics and information in the world. So more and more, you need to actually be able to also absorb multimodal information rather than just text. But in this, again, rest of this talk, we'll stick with the text side of it. So back to the question, so how we can use natural language processing to create knowledge graphs. And here I'm going to start using a piece of text from the Wikipedia, so the first page of the Wikipedia for first a few paragraphs of Wikipedia for this film. So here's a piece of text, and we want to be able to extract information from this and form it in a way that then we can actually query it later on. The first step that often we perform is called name entity recognition. I don't know how many of you actually know about this, but it's a technology within natural language processing where you are trying to read the text and identify entities in the text and put them in a class. So for example, you start from here and you see 2018 and you see date labeled on top of it, then you carry on, you see Han Solo, you say this is a person, you carry on, there is Walt Disney Studios motion pictures, you classify this as an organization, that this is this is an organization in the world, and so forth. So you encounter United States, that that's a country. So this is called name entity recognition, and it's again on the outside for us as humans, this is a very easy task. So if I give you this piece of text and I said that try to find things in this piece of text and label them for me, it's going to be very easy. But again, from a machine learning perspective, it's a complex task because what you have to do is to actually, while reading the text, understand the context, know where actually an entity starts and ends. So, for example, Walt Disney Studios motion pictures is in this 5 words thing, and you have to actually be able to actually piece all of this together, saying that all of this from here to here is actually talking about this one entity. So you are not actually operating on one word, but you're actually trying to infer information out of many, many words. There is context in here, so you have to be able to actually read this and actually understand, disambiguate the type of the class that's referenced. And if I want to actually go a little bit deeper and give you a little bit of the machine learning behind it, so this output space here is called a structured output space because you are not just classifying a given thing as, let's say, one class or the other, but you are actually trying to predict not only the class, but also, let's say in here, the span, from where to where an entity occurs in your text. So it's quite a complex system, and we use deep neural networks to do this in Alexa. The other concept is what we call entity discovery. So all the other things that you saw here, you may have references to them. So there may be things that you know. But if this is the first time that you're encountering solo Star Wars story as an entity, you want to be able to discover this and add this to your catalog. Again, why this is important is that, again, the world changing. We have many new things that gets released, that gets talked about. So you can't just rely on things that you know and always go and extract information about things that you know. You have to be able to discover new concepts, discover new things. This is called entity discovery, and equally is a very, very tough problem to solve because, again, you have to actually understand where in the text this entity is mentioned. You have to classify what class of entity this is. You may have to go through many other websites and many other informations to actually get more information about this and make actually a coherent picture of what this is. So is this a human? Is this a film? Is this a music that is released? So you have to be able to actually infer all of this out of many, many different encounters of the same entity. But it's a very, very important step to actually keeping up with the world that is changing. You have to be able to discover these new entities and add them to your knowledge. The other part that we often talk about is called entity linking. So once you have detected an entity, so in this case, let's say Ron Howard, and you know that's a person, you want to be able to link that back to your knowledge graph and say that, aha, I see here, Ron Howard. So anything that will be, followed here will be about this person. Which again, on the surface, you may want to, match text and say that, okay, Ron Howard here, is written this way, and on my knowledge graph, I have Ron Howard, so I can, match it, and that may get you to some degree ahead. But you have to also know that, for example, Ron Howard could be many people. It's not just, one person. So this is again from Wikipedia. There's at least 6 encounters of Ron Howards, and these are also the famous Ron Howards that made it to Wikipedia. So in your world, you may have even many more Ron Howards. So actually, how do you know which one of these is this, is this document talking about? Is it, is it the professor? Is it the football player? Is it the director? Is it the actor? And this is what we call disambiguation. Again, you have to use all the knowledge that is within your text, within what you know about the world, to be able to correctly disambiguate what is the thing we are talking about. You saw the example of this in the gherkin example. When we talked about gherkin could refer to many things. So how do you know which one is which? That is asked in the sentence. And again, it's a very, very challenging task. You need advanced machine learning techniques to do this. You need to be able to process the graph and have information about the graph, knowing that in your graph, Ron Howard is a person, is an actor or a director and have done, these other films. Based on those contexts, you can then disambiguate correctly that, in this text, we are talking about Ron Howard, the director, not the football player. The other challenge is called entity coreference resolution. So as you see here, the name of the film is mentioned in the beginning of the text, and after that, we easily refer to it by it. So we never, write again that long name of the movie. And again, this is very ambiguous because, when you're reading this as from the machine's perspective, you can encounter it, and then you have to actually infer what this it refers to. Again, for us as a human, this is very natural. We grew up actually with lots of smarts and intelligence to do this almost effortlessly. But for a machine, you have to be able to actually detect what this is referring to. What is this it? Is it referring to the director? Is it referring to any of those fictional characters? Is it referring to the film? Is it referring to American space western genre? What is it that it's referring to? So you have to again be able to do this, and often there's long references in the text. So again, many few sentences down, it is again this is another sentence says it was released in the United States on this date. So actually here you have to again be able to back reference the it here to the original film that was at the top. Once you do this, once you are able to do this, you may want to go to another technique, which is called relation extraction. Now that you know what are the entities in this text, what are the things that we are talking about, you may want to discover what are the relationships that is talked about in the text. So for example, from reading this text, you might say that, okay, directed by Ron Howard, produced by Lucasfilms, distributed by Walt Disney, it is the second Star Wars anthology film, et cetera, et cetera. So here you want to know it refers to the film, you want to know who the Ron Howard is, which is the director, and you want to be able to read this text and come up with such a relationship such as this film is directed by Ron Howard. Again, on the surface, you may see that there's similarity between directed and directed there. So you may say that okay, I may match some text to do this. But again, this falls apart very quickly because many things could refer to many things when you talk about it. So, for example, you may talk about created by Howard, but Ron Howard. You may refer to many different ways. So again, how to be robust to all of these ambiguities? Again, you need to utilize heavy machine learning to be able to look through all the context and make the correct decision. Text is not also represented just by a linear piece of string. Again, on the web, you may encounter things such as tables, which are also, again, great sources of information. So here, for example, there's a table about all the Star Wars films, and again, you see here at the final row the name of the film, the date that was released, and the column header here. Again, this is a great source of information to extract the release date, but as similar to the other cases, the header here may be ambiguous, may be actually not existent in a table. So how do you go about actually looking through the columns here, looking through their content and infer what is the relationship that exists between these two things that's expressed in the table. Similarly, on what we call semi-structured web pages, where it's not just pure text, it's not also pure tables, but it is somewhere in between. So, for example, this is the film listing on Amazon for Star Wars. And you could see, for example, that there is a name of a thing. Down here, there's name of people and directed by. So this is not purely text because it's not a narrative. You can't just read it. But it's not a table neither. But falls within a similar type of context that how I can actually infer from all this information that, for example, George Lucas directed the Star Wars films. So final few areas to cover. So once you have built this knowledge graph through technologies that I showed you, then the question is that, okay, how I can use this within the context of, let's say, question answering. So when you encounter a question such as, when was the last Star Wars movie, how I'm actually going to use this knowledge to actually provide an answer. So these are the predominant stages that we go through. So the first one is called natural language understanding, as I was referring to earlier. This will try to read the sentence and try to understand what are the entities, what are the things that you're talking about in a sentence, and try to form a query, which we call semantic query, to our knowledge graph. So again, when I mentioned earlier, when you get this, what you will try to do is that from here you will look up and say that, okay, here Star Wars movies means the Star Wars series, film series in your knowledge graph. We are talking about, you have a temporal question, we are looking for the last one. So your semantic query here will look more or less like, give me all the films within the Star Wars universe sort them by their dates, and pick the last one from that. So again, this query becomes very, very complex as also you go for more complex questions. So, and the language is compositional, as you know. You can add more and more things as you are talking about the concepts in the world. So, for example, you may want to say, that question, or you may want to say, Alexa, when was the last Star Wars movies that George Lucas directed it? Right? So it's the same question, but now you added another thing to it, which is, the condition that, George Lucas should have directed the film. And because of this compositionality, you can actually go on forever and forever. You might say that, when was the last Star Wars movies that George Lucas directed when I was 14 years old? Right? So you can actually go many, many layers deeper here in terms of the kind of question that you're asking. And all of these are legitimate questions. You may ask that, who's the president of the United States? And you may get a very straightforward answer, but you may say that, who was the president of the United States when Barack Obama was a teenager? You can start, composing actually very, very, weird questions. And again, it's the combination of the advanced machine learning techniques, natural language understanding techniques, and a knowledge graph that enables you to be able to actually cope with all these complexities of the world. And as I mentioned, this system tries to compose a query that you can then send it to your knowledge graph. And again, you coming from technical backgrounds, kinds of queries that I'm talking about. So you've probably written SQL queries or any queries to any database. So you know that how often they're very, very complex. They are very difficult to write and get it right. But imagine that you have a system now that is actually writing these queries rather than you writing it by hand. Because for any of these situations, for any of these different encounters, you have to actually encode all of that in your query and ask your knowledge graph to provide an answer for it. Another part that is here is also, as I mentioned, about the mechanics of the world and how the world works. So, for example, in our knowledge graph, we have all the consistency checks when you ask a question or when you insert any new information into it. So when I say consistency checks, it is, for example, when you talk about Gdansk as a city, you know that Gdansk is part of Poland, but also because of how the world works, you know that the Gdansk can't be in two places at once. I mean, there are cities, of course, that they have the same names, but the particular Gdansk that you're talking about can't be in two parts of the world. So if I tomorrow read from somewhere in the text and on the web that Gdansk is part of somewhere else, I have to be able to actually contrast that information that I've extracted from a source, and then, through those consistency checks, look into, does it match to what I think is true or not? Because it may be that, presidents change, and that's fine. There are elections in the world, and presidents change. But there will be one president at a time in the world. And when such a thing happens, you want to actually also know also from a lot of different sources that really this thing happened or not. So the mechanics of the world, how the world works, actually gets encoded in our knowledge graph, and as I said, all these ontological checks and consistent checks and inferences performed on the fly for all the entities that we absorb. And finally, all the entities that comes back from our knowledge graph, then we have to compose a natural language answer to it. And again, this is a quite complex topic. I'm not going to talk about it, but you can think about, in this case, getting just a film name and composing a natural language answer, as it was with the Alexa, that this was the film, and it was released on this date, and so forth. Again, it's quite a complex topic, and you need, again, heavy machine learning to be able to do that. One final thing, and this is, I think, one of those reasons to use knowledge graph, is that because of the facts in the world, they are really factual, and no matter in which language you speak, world is the same. We have one world that we live in. As a result, when you have extracted information from web or any other sources, and you've encoded in a semantic graph, you should be able to access to that from all different languages. So, for example, if I have extracted that this film was released in this date, and if somebody comes and asks this same question in French, The only thing that changes in between is that we have French natural language understanding systems that can interpret now French language rather than English. But the output of that will be exactly similar to the output of the other one, because it's the same kind of query that has to go through RAF. What this means is that when I spoke earlier that the Alexa is now available in so many countries, all the information that we extract from all the sources is immediately available for all these languages, because only thing that changes really is the information under the hood, and all these different language understanding systems are able to make the same query to the knowledge graph. So knowledge graph in that sense are great for scaling your technology to many, many languages. And finally, web being web is quite noisy. And especially since a few years back, maybe more, depending on your perspective, there are a lot of information that's not consistent, that is not factual, that may contradict each other. And more than often, there are bad actors in the world that they want to introduce noise, introduce non-factual information to our ecosystems. And as a global device, we have to be able to actually cope with this noise. We have to be able to actually be factual, be consistent. And it's also a big part of the research that we do in the Cambridge office in the UK, working on algorithms that are able to verify when a fact is stated. So if one of our algorithms is extracting a fact, we will have these fact verification systems that are able to automatically score this in terms of their factuality and trustworthiness in the world. We've been running a workshop as well. This year is going to be second time, called Fever, which again addresses this topic because it's a very, very challenging one, and even in the academia, it's not truly solved problem. We've been organizing this since last year. This year is the second one, which really tackles this topic. And again, if any of you are interested, you can check and participate. Cool. So that is coming to the end of my talk. I think I talked too quickly because I think now I'm seeing on the clock over there, and I still have 20 minutes to talk. But basically, this is my last slide. I think the future is going to be very, very different. We are going to have many of these smart devices anywhere in the world, in many of our environments. So from technology perspective, it's actually a very, very big challenge to be able to create these robust devices at a large scale, and that is the mission that we have in Alexa. Cool. I'll finish here, and then we'll have plenty of time to question and answer.
One. Any questions? I hope yes. Yes.
The question is, how do you moderate the data? So as you told, there is great amount of noise, and what is the percentage of manual labor there, like mechanical Turk's work?
I'm not sure about the entirety of how much mechanical Turk gets used, but I know that we internally do a lot of annotations to moderate basically the content, and as I said, we have a lot of automated systems that will reject many of these facts. But I think in terms of things that are not solvable by those systems, we will have people actually verifying these data.
Maybe from the right, because my friend is over there waiting.
Here. Some questions?
First of all, thank you very much. It was very interesting.
Thanks.
And I wanted to ask, for these things that you said, you are monitoring, as I think, from the media, what's happening, what is true, what's not. Do you also need some people for the media monitoring, or just for analyzing the content, what's happening in the news, or just you need some people for machine learning? Do you cooperate with media, or what kind of specialists you need?
I don't know about the again all the details, so I'm not the right person to be able to answer that. Again, for us, when we extract information, we try to extract them from sources that we know they are trustworthy, and that means that there's a good reliability to what they talk about. But all in all, I mean, noise can get anywhere, and even like sources like Wikipedia, which we may think that is a should be very, very factual, sometimes have noise, and you need to have as I said, mechanisms to prevent that from becoming part of your knowledge. So again, we have a lot of automated methods. We have some manual methods to cope with this.
Some other question?
As we are waiting for Stefano because he is getting ready, we should have like 2 more questions.
Thanks. So my question is regarding update of some not really static data. For example, I don't know if someone asks about result of election in 2 minutes after result was published, how do you trigger update of this graph, or this is a question?
So for some of these very special events, we have also certain algorithms that gets developed for that event. For example, there was a election in India that, and it's in the news, you can go and watch it, that basically actually Alexa device was part of the newsroom, so they were actually asking Alexa to update them on what's happening. So sometimes they basically, for such events, they build dedicated systems to do it. But more these days, our systems, I said, we don't try to pick up on very, very quick or very, very sensitive information that quickly. Those goes often, as I said, through specialized sources.
I am happy that the right side got more active. Any question maybe from the left?
Left-hand side, give me one more.
Yes. Perfect.
I wonder how this is related with the search engines working. So, and I believe they are really related. So in that case, I really wonder how we are competing with Google in this area.
That's a very good question. So as you rightly say, the space of being able to answer questions is the same space as search. So when you go to any search engine and you try to input a question, you're expecting the same kind of answer. I think there are a few differences in terms of Alexa herself. It's when you go to Google or Bing or any search engine, you often get presented with a list of possibilities. So it is recommended, first link, second link, and you can go many pages deep, which is not the same with Alexa. So in this case, because there's just one channel to express the output, you have to be able to actually pick really the best answer and bring that forward. So there are challenges there in terms of needing to be a lot more high accuracy than normal search engines. Because again, in the search engines, you have the option that you can go down if the first link wasn't correct. In terms of the underlying technology, there are some similarities as well, of course. When you are reaching out to web, you need to be able to look into a lot of same sort of information. It's very large scale. You have to be able to index them. There are all these basic similarities, but in terms of, again, the technology being used, there are also very, very different techniques that's needed for this.
Okay, Alexa told me that Stefano is ready. So Amir, thank you for the presentation.
Thank you.
My dear audience, thank you for the questions.